Okay, so in this video, it'll be a test review for on angular momentum for the tests we are having tomorrow. So the first question, it looks like this. There is a spinning disk. This is bird's eye view. This is it from the side. There's an object, the blue object coming in this way and the red object coming in that way. And this is what it looks like on the bird's eye. And our goal is to figure out how far the blue object landed from the center of mass, or the R is what you can call it. So how do you do this? Well, you can set up the L initial for the, we'll say L1 is the red one, plus L initial of 2, which is the blue one, plus L initial of the disk, equals our L final, right? So now let's set this up. L initial 1, so what is that? That is our red one. So we can set it up, and also we know the red one is going this way and the disk is spinning this way, so they're going to be, it's going to add more momentum to it. So we have our we can do RP sine theta equals IW, right? However, here we don't use sine because we'll look at it like this. It's coming in like that, and it has its two things, and this is the angle given, and it coming, the sine of this is coming straight down, but that isn't going to affect the actual momentum of the thing. What will affect it is its horizontal motion, so it'll be cosine of this angle to get this. So how do we set this up? Well, our R for red is given as 0.4. Our P, what is P? P is MV, so M 3.91 times 3.10. That's RP, and then instead of sine, we're just gonna use cosine 47, right? So that is for L1, then plus our L2. What is L2? What is the blue one? So the blue one is going left, in the left direction. So if we're gonna say the positive direction is right, that means left is gonna be negative. So we're gonna do plus negative, right? So we don't forget the negative. And same thing. So R, which is our variable, so we're gonna do R times P sine, or P cos theta. P is M 5.25 times velocity 14.5 times cosine its angle 12.6, right? Plus our last one, which is going to be, instead of RP sine theta, it's easier to do IW, which is the disk. So it'll be 1/2 M, which is given 62.5, R squared 0.441, square that, times its W initial is 6.20. So once you have all that set up, we can pretty much equate that to the final. So equals, and our L final. So what can we do? We can do all our inertial inertias added up times the W. So we can do in brackets. So our first one, we can just do 3.91 times 0.4 squared, because MR squared, plus 5.25 times our R variable squared, plus 1/2 M 62.5 times 0.441 squared, and that's our I, times W, which is our W final, 3.45. Now, once we have all that, just plug it in a solver, and you should come out to R equals 0.228 meters. And that is how to do a question like that. Okay, for the next one, it is going to be, there's a bullet that is here, and it is fired at a velocity of 366 meters per second, and it comes into this disc right here, and it is going to pretty much, it's going to hit it, and it's going to spin around this rotational axis that it's connected by. So there's a wire here, and so let's say it's here, it's going to be hit, and it's gonna, let's say it's here, it's gonna boom, hit, and it's gonna spin around it like that. And our question is to find the tension in this red wire right here. So how do we set this up? Well, again, we do our L initial plus L initial equals L final. So, and also we have to notice that there is a displacement in where the actual axis is. So we can use the parallel axis theorem here. And yeah, so let's start. So our first one is initially this is not moving at all. So what is it? It is going to be 0. Our IW is 0. Plus, now we can talk about the bullet. So the bullet, we can use RP sine theta. So our R is going to be, instead of just 1.22, it's going to be 1.22 plus the R of this, which is 0.04. So 1.22 plus 0.04, because it's, it comes here, so it's the full length from the axis, times M, which is 0.00260, and then times V, 366.0, and it's going to be sine of our angle that it comes in at, sine 72.5. Sorry for this pen. 72.5 is the angle, so that's what it is, and it comes boom, and also up. So if we're wanting to find, which way it's perpendicular to this radius, it's going to be using sine to get this, because it's hitting it like that, not like that. Okay, now we can equate that to our L final. So first we have our, so now that it's hit, it is going to be moving. So we have 1/2 times our mass, 0.241, times radius, 0.04 squared. So 1/2 mr squared, right, for the disk, plus, now this is where the rotation parallel axis theorem comes in hand. So it's offset, so it's going to be md squared. So our m is going to be, again, 0.241, since this is massless, the wire, that's m, times our distance, which is 1.22 plus 0.04, right? It's that entire distance. So square that, so that's our rotation axis theorem, plus the bullet final. So that is going to be 0.00260 times 1.22 plus 0.04, square that, and that is all going to be multiplied by our W final. So now, once we set that equation up, we can solve for our only variable, which is W final, right? And our W final should come out to 2.96 radians per second. Now, since we have our W final and we're looking for the tension, we have an equation for that. So what it is tension equals centripetal force. So what does centripetal force equal? Well, it equals mW squared R. So using this, we can find the tension in this wire. So let's plug it in. So tension equals our mass. Well, what is our mass? So our mass is going to be both these masses combined, the 0.0026 plus the mass of the disk. So 0.241 plus 0.00260. So that's our M. Our W is 2.96, and it is squared, and it is going to be multiplied by the radius. Well, what is the radius? Once again, it's the entire length. So 1.22 plus 0.04. And that is how to find tension, which you add this up, and it should come out to 2.69 newtons. And that is the tension in the wire. Okay, the next question is pretty much asking what is the work required to get to RF, and you are pretty much, you're starting here at the outside of this disk, and you are walking inward, and it is asking, what is the work required to get there to the RF, which is 1.85 meters. So what can we do? Well, we can first set up our equation to solve for W final. So that is what we're looking for first. And then we can set up our kinetic energy equation, which is 1/2 I W squared. So we can set this up. So we have our 1/2 122.5 mR 4.25 squared times W initial of 2.35. That is going to be plus the other IW, so mR squared, so 62.0 of the person that's walking. It's a point mass, so mR. So we're going to do our I initial as 4.25 mR squared times the same 2.35 W initial. So that is our initial, and that is going to be equal to the final, which is going to be 1/2 122.5 times 4.25. The disk doesn't change, times the W final, and that is going to be added to 62.0. The R here does change, however, it goes to R final, which is 1.85 squared times W final. So we can plug this in solver, and we come out to W final equals 3.97 radians per second. So that is our W final. Now, using that W final, we can pretty much do the kinetic energy difference to find the work required. So we can do the kinetic energy final minus kinetic energy initial. So we can use the equation 1/2 I W squared final minus 1/2 I W squared initial, and that equals our work required. So what is our final? Let's set it up. So 1/2 times our I, which is 1/2 of the disk, times 122.5, so 222.5 times 4.25, square that, plus 62.0 times, we're using our final, so it's going to be 1.85 squared, and that is all in big parentheses, and it's going to be times our W final that we just solved, 3.97 squared, because it is I W squared, and that is going to be equal to 1/2 the I W squared initial. So again, 1/2, this doesn't change, times 122.5 times 4.25 squared, plus 62.0 times our initial of 4.25 squared in big parentheses times our W initial, which is 2.35 squared. And this is not an equal sign, this is a subtraction sign. And that is going to equal our work required, which should come out to around 4240 joules. And that is how to do a question like